Welcome to Your Math Explained, where we make math simple and clear. My name is Angela. In today's video, we'll break down why the chain rule works through the definition of a derivative. And we'll also look at one interesting property that arises from the chain rule. Now, before we get started, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. Now to start, to prove the chain rule through the definition of a derivative, we're going to start with d by dx of our composite function f of g of x. And the definition says this is equal to the limit as h approaches 0 of f of g of x plus h minus f of g of x over h. And now the trick here is we're actually going to split this up into two fractions. So this is going to be the limit as h approaches 0 of f of g of x plus h minus f of g of x. And then for this one, we're going to put this over g of x plus h minus g of x. And then we're going to multiply this by g of x plus h minus g of x over h. And we know we can do this because essentially we've just multiplied it by 1 and then reorganized our fractions. And now because both f and g are differentiable, both of them are continuous. And the limit law says that we can split this up into two separate limits. The first one being the limit as h approaches 0 of f of g of x plus h minus f of g of x over g of x plus h minus g of x. And we multiply this by the limit as h approaches 0 of g of x plus h minus g of x over h. And now the second part, that is just the limit definition for g prime of x. So this is g prime of x. Now for the first limit, we are going to do a clever substitution. So we're going to let k be equal to g of x plus h minus g of x. Then we can see that the limit as h approaches 0 for k, well, that's just equal to 0 because that's going to be g of x minus g of x. And we can also see that our numerator, which is f of g of x plus h minus f of g of x, well, that is actually just equal to f of g of x plus k minus f of g of x. And we can do some quick algebraic manipulation to show that's true. So if we substitute k into here, this is f of g of x plus g of x plus h minus g of x. And then we have minus f of g of x. So here we can see that we have g of x minus g of x, so they get canceled, which means this is f of g of x plus h minus f of g of x. So why is that important? Well, it allows us to rewrite this, so that means we get d by dx of f of g of x is equal to, and now we can write this as the limit as k approaches 0 of f of g of x plus k minus f of g of x, and this is now over k. And that is multiplied by g prime of x. But now if we look at our first limit, this is now the definition of a derivative for f prime of g of x, right? Because we have g of x plus k in here, and then here this is just g of x, and then this is over k. So which means this is now equal to f prime of g of x times g prime of x. And thus, we have now proved the chain rule. Now, there is a small caveat here, which is what happens when g of x plus h minus g of x is equal to 0. And there is a more rigorous proof that deals with that particular case, but that's beyond the scope of this video. Next, let's take a look at a problem where we have some interesting properties that arise from the chain rule. A function f is called an involution if f of x is equal to x for all x in its domain. So in other words, it is a self-inverse function. For part A, we want to show that for any point AB on the graph of an involution f, then it satisfies this relationship here. To do that, we're going to start with the property of an involution, which is that f of x is equal to x. Next, we're going to take the derivative with respect to x on both sides of this. So this means d by dx of f of x is equal to d by dx of x. Now the left-hand side, we're going to have to use chain rule. So this ends up being f prime of x multiplied by f prime of x, and then the right-hand side, that is equal to 1. And this is going to be true for all x in the domain of the function f. So now a comma b is a point that is on f. So this means that f of a is equal to b. So that tells us at the point x is equal to a, we would have f prime of a times f prime of a is equal to 1. But since f of a is equal to b, we can go ahead and substitute that in. So that means we get f prime of b times f prime of a is equal to 1. And thus, we have shown that this relationship is true for any point AB on the graph of f. Now for our next part, we want to look at a specific involution where f of x is equal to the square root of k minus x squared. And the domain for this is x is in between 0 and root k. So first, we're going to verify that this is, in fact, an involution. So that means we start with f of x, and substituting in this particular function, this is going to be f of the square root of k minus x squared, which means this is equal to the square root of k minus, and then we're going to have the square root of k minus x squared squared. So squaring a square root is just going to cancel it, which means we get this is the square root of k minus x squared. Simplifying what's under the square root is going to give us this is the square root of x squared, which is just equal to x. And notice that we only get positive x because our domain is from 0 to positive root k. So this is part 1. And now for the second part, we want to use the result from part A to show that if f prime of x is equal to -1, then we get x is equal to f of x. First, let's take a look at what f prime of x is. So we're going to take the derivative of f of x, which means f prime of x is equal to 1/2 times k minus x squared to the power of -1/2 multiplied by -2x. Now simplifying this is going to give us negative x over the square root of k minus x squared. So now if f prime of x is equal to -1, then that means -1 is equal to -x over the square root of k minus x squared, which means the square root of k minus x squared is equal to x. And if we actually solve this, we end up with x is equal to the square root of k over 2. So notice how we only have one solution here. So that means there's only one value within the domain where the derivative is equal to -1. Now tying this back to part A said that f prime of f of x multiplied by f prime of x is equal to 1. So if f prime of x is equal to -1, then that means f prime of f of x must also be equal to -1. But since we know that there's only one value within the domain where the derivative is -1, that tells us that this f of x here, this must also be that particular value, which is the square root of k over 2. So therefore, x is equal to k over 2, and f of x is also equal to k over 2. Which means if f prime of x is equal to -1, the only place where that occurs is when x is equal to f of x. And now for the last part of this question, we want to show that the second derivative of an involution satisfies this equation here. So we're going to start with the result from part A, and we're going to differentiate both sides with respect to x. So from part A, we know that f prime of f of x multiplied by f prime of x is equal to 1. Now we're going to take the derivative with respect to x on both sides of this equation. So we go d by dx of f prime of f of x multiplied by f prime of x. And this is equal to d by dx of 1. Now the right-hand side is easy because that is just equal to 0. But the left-hand side, we're going to have to apply our product rule. And the product rule says we're going to go d by dx of f prime of f of x. And then we're going to multiply this by f prime of x. And then we have to add f prime of f of x multiplied by the derivative of f prime of x. And that is going to be equal to 0. So let's take this derivative first. And here we're going to have to use our chain rule. So this is going to be f double prime of f of x multiplied by the derivative of the inside function. So that's f prime of x. So that is that derivative right there. And then we multiply this by f prime of x, which is just us copying this part down. And then we add f prime of f of x multiplied by, now the derivative of f prime of x is just going to be f double prime of x. So that's that part. And this is equal to 0. And now the last part is just to simplify. So we have f prime of x times f prime of x, so we can rewrite that as f prime of x squared. Which means our final answer here is going to be f double prime of f of x times f prime of x squared plus f prime of f of x times f double prime of x is equal to 0. And that is exactly what we're trying to show up here. And so this is where we would stop. And now let's do a quick recap of what we covered in this video. First, we went over the proof for chain rule, and like all the other derivative rules we've seen so far, it's generated from the limit definition of the derivative. Then we went over an interesting problem where chain rule was used to find properties of derivatives even when the function f of x wasn't explicitly defined. And now it is your turn to give this a try. Can you find the solution to the problem on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.